Hello everyone, in this video we'll talk about regression. The topics which we are going to cover are, we will be starting off with the regression problem in a very simple one dimension, which will help us to define terms like predictor variables, response variables. Then we'll see how we can convert this problem into an optimization problem by properly defining a loss function. Then we'll find out how we can come up with an optimal solution to this minimization problem. As a next step, we will be trying to generalize this problem with multiple predictor variables, which will come to least square regression, and we will see the statistical interpretation of regression as well. So linear regression is nothing but the job of fitting a line onto a bunch of points. So see here, there are few red data points. You are supposed to come up with a regression line which almost pass through the middle of these points. Since there is no such line which actually pass through all these points, we would like to come up with a line which passes through the middle. There are let's see why we would like to do this and how we are going to do this. Let's take an example first. Let's say at some college or university, they have collected the semester grade point average SGPAs of all the students of some particular course, and they have plotted a histogram of this. In the x-axis the SGPA of students, in the y-axis its frequency, so you will get something like this. Okay, so what will happen if a random student comes up and we would like to predict his GPA? Without any further information, we can directly predict the mean of this distribution, right? In this case it is 4.67. So next we will see how good is this prediction. Or what is the error in this prediction? We would like to find out the average squared error of this prediction, that is the expected value of the error, squared error. It is expected value of student SGPA minus the predicted SGPA square. It turns out that it is nothing but the variance of the distribution. Okay, so let's say the university has collected some other feature like the student's entrance score from his previous course or previous semester, and they have plotted it as a scatter plot. Entrance score in this case I have plotted it as in the normal scale, normalized value, and then score in the x-axis and SGPA in the y-axis. So you can see that there is a positive correlation again between end score and SGPA. You can very well come up with a regression line which almost pass through these points, the middle of these points. So the average squared error, the mean squared error, you can see that by introducing another feature end score, you can see that the average squared error or mean squared error which drops compared to the previous example. In this case, the variable which helps us to predict is called a predictor variable, and the variable which we are predicting is called a response variable. The SGPA is the response variable and n score is the predictor variable. So this is a classic regression problem with this predictor variable and response variable. So as we have told, it's a line fitting problem. We can parameterize a line as y equal to ax plus b, where a is the slope of the line and b is the y-intercept. For example, in this case, the slope is minus 1 by 2 and y-intercept is 1. So this line can be written as y equal to minus 1 by 2 x plus 1. So the line fitting problem can be written like this. You pick a line, means you find out parameters a and b suited to the data x1, y1, x2, y2, etc., xn, yn. All this belongs to real R cross R, where xi is the predictor variable and yi is my response variable. Xi is the end score of the ith student and yi is the end score SGPA of the ith student. The formula for mean squared error can be written as sum over I yi, which is the actual value, minus axi plus b, which is the predicted value. So actual minus predicted, the whole square, sum over all the data points I equal to 1 to n, then divided by n, means you are taking the average of the squared error for each of the data point, which is nothing but the mean squared error. So we would like to minimize this mean squared error, or we would like to find out parameters a comma b such that this mean squared error is a minimum. So this problem now converted into an optimization problem where this function can be termed as loss function. So instead of mean squared error a comma b, we can say this is a loss function. So we would like to minimize the loss function. Given x1, y1, x2, y2, etc., xn, yn, minimize the loss function a comma b 1 by n sigma I equal to 1 to n yi minus axi plus b the whole square. To minimize, we will set the derivative dl by dA equal to dl by dA equal to dl by dv equal to 0. You get the solutions like this: b is equal to y bar minus ax bar, a equal to sigma I equal to 1 to n yi minus y bar into xi minus x bar divided by sigma I equal to 1 to n xi minus x bar the whole square. You can see that there is a nice closed form solution for b and a. Right. Next we'll try to generalize this. That is, let's talk about a linear function of 10 variables. Means x belongs to R10. Linear function of one variable, we have written it like y equal to wx plus b. If you have 10 variables, then we can write it as the linear function can be written as f of x equal to w1 x1 plus w2 x2 plus etc. w10 x10 plus b, the y intercept. Or even you can write it like this: w dot x plus b, where w is w1, w2 etc. w10, this vector. You penalize this expression by using the squared laws: y minus w dot x plus b the whole square, that is the squared laws. You can come up with the loss function also here. The least square regression is defined like this: given data x1 by 1, x2 by 2 etc., xn by n, where x is d-dimensional and y is one dimension. This data belongs to R d cross R. What we would like to find out is w, which is a d-dimensional vector, and b, a value, a real value. The goal is to minimize this loss function yi minus w dot xi plus b the whole square. Here also you can find that there is a nice closed form solution for w as well as b. Okay, next we will see the statistical interpretation of regression. In statistics, we can form a reasonably good linear equation by projecting x values to y or y values to x. The regression equation of y on x is given by y minus y bar equal to byx into x minus x bar, where byx is the covariance of xy by variance of x. The opposite, the regression equation of x on y is given by x minus x bar equal to bxy into y minus y bar, where bxy is the covariance of xy divided by variance of y. Okay, so next you open Colab, do a simple exercise based on linear regression. You upload the data, upload salary data, from statistical models.api, import statistical models and pandas. Using pandas.readcsv, you open the data set salary data.csv. Then you create in the salary data also you have only two columns. The first column is taken as the X value and the second column is taken as the Y value. Then you create a model. From the statistical model you open ordinary least square regression. You note the difference in argument y to be given first, then x. So sm dot OLS yx dot fit, and you can go for predictions. Once you create the model, you see that the model summary can be seen. Model is OLS, method is least square, number of observations, total data, and so many things. See, from sklearn, scikit-learn, you import linear regression. Then you fit the same x and y values to sklearn's linear regression. You can see that the data is plotted in blue as a scatter plot, and the regression line is plotted as a red line. The x-axis shows number of years experience and y-axis shows the salary. Okay, in the next video we will see principal component analysis.